Morning, everyone. How are we doing? Absolutely. Yishen is asking to find the Maclaurin series for tangent. Can we use the Maclaurin series for sine and cosine and do long division? Absolutely correct. You know that sine has Maclaurin series x to the 2n plus 1 over 2n plus 1 factorial. So in other words, this is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5 and so on. Cosine has Maclaurin series negative 1 to the n x to the 2n over 2n factorial, which is 1 minus x squared over 2 factorial plus x4 over 4 factorial and so on. So tangent, which is sine over cos, is therefore x minus 1 over 6x cubed plus 12, 24, 120. 120x to the 5 divided by 1 minus x squared over 2 plus x to the 4 over 24. So if you do long division, in other words, x minus 1 over 6x cubed plus 1 over 120x to the 5 divided by this, so we ask the question, what must you multiply to 1 to get an x? The answer is x, and then you get an x minus x cubed, or 1/2 x cubed, plus 1 over 24 x to the 5, and then you subtract. This minus this is 0. This minus that, so 3 minus 1 is 2. There's going to be a 2 over 6 x cubed. This minus that, whatever that is. And then you repeat. What must you multiply to 1 to get a 2 over 6x cubed? Well, that's going to be 1/3 x cubed. And you repeat. And consequently, if you keep going, the Taylor series or the Maclaurin series for tangent x is going to be this, x plus 1/3 x cubed, and so on and so on. A very nice observation. And yeah, you could, of course, find the Maclaurin series the usual way, right? Derivative of tangent, tangent of x, tangent at 0, derivative of tangent, derivative at 0, and so on and so on. And the two answers will agree. It's not clear in this case that you can find a nice pattern arising, but some functions don't have a nice closed form. It is what it is. There are many other questions that, let me scroll back up here. If you have questions about your 141 final, email me. We are looking for the Taylor series of cosine at pi over 3. You could do something with this. Let me not give it to you. There's something that can be done with that, but if you're looking at Taylor series of cos x around right, you know what to do. We're going to do it the long way. Cos x, and then your function at pi over 3. Cosine of pi over 3 you know to be 1/2. The derivative is negative sine. The derivative at pi over 3. Sine of pi over 3 is root 3 over 2. So negative root 3 over 2. Second derivative at pi over 3. And you keep going until you see a pattern arising. You know that the fourth derivative is going to come back to cosine, so you're going to have that pattern arising. But there it is. So this is negative 1/2, and so on, right? So your function f of x is f of c plus f prime of c over 1 factorial x minus c. Second derivative over 2 factorial x minus c squared, and so on. So in this case, cosine 1/2 plus negative root 3 over 2 over 1 factorial x minus pi over 3. Second derivative over 2 factorial x minus pi over 3 squared, and so on. There it is. Here it might be slightly awkward to find a pattern. So oftentimes these questions only ask for the first few non-zero terms. I suspect that's what it was asking for here. Nima is asking, could we please explain why we compare 1 over x when trying to prove the convergence of ln x over x? Well, I suspect you mean if you're trying to prove the convergence of ln n over n, we're going to do a comparison test with the series 1 over n, right? I mean, you're looking at this and you're thinking to yourself, well, the denominator behaves like n, so we're good to go. Numerator is ln n, and you know ln n is an increasing function. So this whole thing is going to be bigger than 1 over n eventually. And that's the idea. Right? As soon as n is large enough, this is going to be bigger than 1. So for n large enough, right, because this keeps increasing forever, going off to infinity. So ln n is going to be bigger than 1 eventually. Right? In fact, if n is bigger than or equal to 3, this is the case. And consequently, ln n over n is going to be bigger than or equal to 1 over n. And you know this series diverges. So the bigger one has to diverge as well. Amar is asking, is there a way to prove the convergence of the series 1 over n factorial by using comparison or limit comparison? There is. The easy way is ratio test, of course, but if you want to use comparison test, let's do it. Right? 1 over n factorial is 1 over n, 1 times 2 times 3, all the way to n. And the number that comes before n is, of course, n minus 1. So this is really 1 over 1 times 1 over 2 times 1 over 3, all the way to 1 over n minus 1 and 1 over n. So, first of all, this is bigger than or equal to 0. And all of these fractions here are all less than or equal to 1. So let me replace all of these by 1, except the last two. So you get that 1 over n factorial is less than or equal to 1 over n times n minus 1. And this series converges. You can do a limit comparison test with 1 over n squared, or it's really a telescoping sum, and you can actually show that it converges to whatever you want. Well, not whatever you want, but depending on where you start. So the series 1 over n times n minus 1, do a limit comparison with the series 1 over n squared, which is a convergent p-series, or you can do a telescoping sum. Either way, this is going to converge, and if the bigger one converges, then the smaller one converges. Now, of course, these tests only tell you that the series converges or diverges, but now you're smarter than that. You know exactly what this converges to, namely, converges to E. Lynn is asking, use the sum of the first 10 terms to approximate the sum of the series. Estimate the error. And the series one to infinity. Cosine squared n over 5 to the n. I believe that's the question. So using the first 10 terms, approximate what the series converges to. And find the sum. Is that, no, sorry. And estimate the error. A nice question. Well, I mean, the first part, you know what to do. You're going to just add up the first 10 terms. So 1 to 10. And that's it. So, using a calculator or using Wolfram Alpha, whatever, this is going to give you a numerical value, and that's going to be your approximation. Now, the question is, how far away are you from the actual answer, right? What is the difference between this and that? Well, I mean, the usual way is that, the usual argument, there it is. Now, the problem is, here, this is not an alternating series, so you cannot use the alternating series business. Integration, well, it's going to be difficult. It's going to be difficult. So the book does something we did not discuss, but I mean, it's not beyond you. What do you know? Cosine squared is always less than or equal to 1 and bigger than or equal to 0. So if you divide by 5 to the n, this whole thing is less than or equal to 1 over 5 to the n. And now you've got a nice geometric series. A nice geometric series that converges. So this is the first term over 1 minus 1 over 5. And there's a nice upper bound on your error. The error is less than that, which is a very small number. Very nice. So Brun is asking the question, how would you go about showing e to the 1 over x squared? Well, I mean, what we suggested last time, it's actually e to the minus 1 over x squared for x bigger than 0, and 0 for x less than or equal to 0. It's a nice question. So this is a question in the book, and they are telling you that this function has a Taylor series which does not converge to the actual function itself. And I mean, I say Taylor series, but it's really Maclaurin series, right? It's a Taylor series around 0. Why don't we take a moment? First of all, the obvious question arises, is this even continuous? I mean, let's not even talk about differentiability yet. Is this continuous? And let's calculate the limit as x goes to 0 from the left. Well, I mean, that's easily seen to be 0. What about the limit from the right? And that is e to the minus 1 over x squared. As x goes to 0, this goes to 1 over 0, which is some sort of infinity. In fact, since it's squared here, it's positive infinity. With that negative makes it negative infinity, and e to the negative infinity is 0. All right. And of course, f of 0 is 0. So the function is continuous at 0. What about the derivative? Just because it's continuous doesn't mean it's differentiable. Is the function differentiable at 0? What is the derivative at 0? Well, let's work it out. if you, well, so what is the derivative? It's the limit as h goes to 0 of f of 0 plus h minus f of 0 over h. F of 0 is 0, so there's no issue there. What is this business? If h is less than 0, so let's calculate the limit as h goes to 0 from the left. What is this? For negative values of h, the function is 0. So that limit is 0. So if the derivative exists, it has to be 0. But I mean, we still need to make sure that this limit exists. F of h is e to the negative 1 over h squared. So as h goes to 0, this goes to infinity. E to the negative infinity is 0. And this is 0. So now you've got a 0 over 0. You can apply L'Hopital's rule. Do I want to do that? Let's do it. I was thinking maybe I would want to rewrite this somehow, but let's not. E to the negative 1 over h squared times the derivative of the inside, 2 over h cubed. The derivative of the bottom is 1. Yeah, that's not very nice. That's not nice. Let's try something else. What do I want to try? If I rewrite this as 1 over h e to the 1 over h squared, does that make it easier? And as h goes to 0, this goes to infinity. E to the infinity is infinity, and that goes to 0. So let's investigate the limit as h goes to 0 of h e to the 1 over h squared, which has the form 0 times infinity. I feel that we're going to be running around in circles here. E to the 1 over h squared over 1 over h, the typical trick. And this now has the form infinity over infinity. And the derivative of this is e to the 1 over h squared times negative 2 over h cubed. And the derivative of that is negative 1 over h squared. Which is just 2 e to the 1 over h squared over h. Okay. This is h plus. So what is this? This is, have I made a mistake there? This is 2 over h times e to the 1 over h squared. Perhaps I had that here. I might have had that here. I just didn't see it. As h goes to 0 from the right, this goes to infinity. This goes to infinity. E to the infinity is infinity. So the whole thing is infinity. Here we go. The whole thing is infinity. So this business goes to infinity. 1 over infinity is 0. Here we go. Got it? So the derivative is 0. At 0. What are we saying? What are we saying? We are saying that if you consider the function e to the minus 1 over x squared for x bigger than 0 and 0 for x less than or equal to 0, we worked out, well, I mean, f of 0 by definition is 0. We just worked out the derivative at 0 to be 0. And in that same fashion, right, so first of all, what do we say? The derivative at any value of x is going to be 0 if x is less than 0, right, because it's just a straight line. At 0, we calculated it to be 0. And then for values bigger than 0, then it's just a usual derivative times 2 over x cubed. And now you can show that this function is also continuous at 0 and also differentiable at 0. And it turns out that its derivative is 0 as well. And in fact, all the derivatives turn out to be 0. So this function has a Taylor series which is 0. It's the 0 function. The Taylor series is the 0 Taylor series, right? It's 0 plus 0x plus 0x squared over 2 factorial and so on and so on. And that series, of course, converges everywhere. But it does not converge to this function. Well, yeah, it does not converge to this function for values bigger than 0. That's what's happening. If you look at the graph of this, the function is 0, and it's very smooth here. Very smooth at the origin, meaning that you can differentiate the function infinitely many times, and the derivative is still 0. That's what's happening. Lyra is asking if I'm going to post solutions for 141 final. I am not. Yishen is asking to find the Maclaurin series for ln of 1 plus 2x squared, I assume. It's better to find the Maclaurin series for ln of 1 minus x by first integrating 1 over 1 minus x and then substitute not the n's but x with 2x squared, precisely that. Or is it better to integrate 1 over 1 plus 4x squared first? Or is it better to find the series for 1 over 1 plus 4x squared and then integrate this? It will not give you ln of 1 plus 4x squared, right? It's going to give you an inverse tangent. Convince yourself. In the book, there is a list of Maclaurin series. Can we simply state them during a test? You cannot. During a test, I want you to show all your work. If you are going to use a Taylor series, then you should derive it somehow. I think Fiona's asking the same question. I skipped too far ahead. No, here we go. Carl's asking what would be the pattern in the cos x example. Yeah, I don't know. I don't know. I don't know. Well, let's not worry too much about it. Yeah. You could split it up into two pieces, right? The odds are either going to be 1/2 or -1/2. So these could alternate. And the evens are either going to be -√3/2 or +√3/2. So you could alternate those as well. There's the pattern. Ryan is asking, can we also say we're comparing ln n over n to 1 over n because n at the bottom is dominant as the n goes to infinity? Exactly. And the numerator is increasing, so it's going to be bigger than 1 at some point. Precisely that. Vivian is asking if we can use induction. You don't need. Did you mean for the derivative? Probably. You can probably prove the derivative is 0 at 0 using induction. Very nice. Ahmad is asking, can't we take the known Taylor series or Maclaurin series for e to the x and plug in 1 over x, -1 over x squared instead? It's tempting. It's tempting to do that. And that's what a student had sent me yesterday who was trying to do that. It's very tempting, and let's convince ourselves why this is an issue. You know the Maclaurin series for e to the x is this. And so if you plug in -1 over x squared in for x, what do you get? You get -1 over x squared to the power n over n factorial, which is really -1 to the n over n factorial x to the 2n. Your x has negative powers now. It's in the denominator. This is no longer a Taylor series, no longer a Maclaurin series. This is very useful in other contexts. These are known as Maclaurin series. That you will encounter when you do a course in complex variables. So a Maclaurin series is really an extension of Taylor series, where you have both positive and negative powers of x. Very important, but we're not going to be discussing this in this class. Carl is asking, can we repeat how we knew the derivative goes to 0? Well, we calculated the derivative for that function at 0, right? We made no assumption, but we calculated the derivative at 0, and we saw that it had to be 0. And then my suggestion to you is you can keep differentiating, and you'll see all the derivatives are 0. I mean, I did this example before, so I knew what the result was going to be. You don't know, so you can take the second derivative and the third just to see what happens. And as Vivian suggests, maybe you can use induction to actually prove that all the derivatives are 0. Of course, if you are not familiar with induction, you can forget that, but it's probably possible to do it. Anna Maria is asking us to use series to evaluate a limit. I was going to do an example of that anyway, so let's do this one. It's a nice exercise. All right, let's start with this. Arctan of x. Let's start by taking the derivative, which you know to be 1 over 1 plus x squared. You know where this is going. You recognize a geometric series, right? And this is 1 over 1 minus negative x squared. So that is negative x squared to the n. Or, if you prefer, negative 1 to the n, x to the 2n. That is so this is the Maclaurin series for the derivative of the arctan function. So now integrate. Integrate term by term. Arctan is going to be the antiderivative plus maybe some arbitrary constant. But the antiderivative of this, you know exactly what that is. So this is negative 1 to the n, x to the 2n plus 1 over 2n plus 1. Plus some arbitrary constant. And this is centered at 0, so 0 is in the interval of convergence. And when x is 0, arctan of 0 is 0. Every term here is going to be 0, right? Because the smallest power of x is x to the 1. And then you have x cubed and x to the 5 and so on. So that's going to be 0. So c is easily seen to be 0. So arctan has Maclaurin series x minus x cubed over 3 plus x to the 5 over 5 minus x to the 7 over 7, and so on and so on. So now, add this business, right? This is a polynomial, and a polynomial is its own Maclaurin series. Isn't that a nice observation? Right? This is a Maclaurin series, a finite Maclaurin series, and it's equal to the function. This function is its own Maclaurin series. X cubed plus minus 3x plus tangent plus arctan is what? Oh, sorry. I should be multiplying this by 3. So plus 3 arctan, right? I mean, I want the 3 arctan. So that's going to be x cubed plus minus 3x. And multiply this by 3. So plus 3x minus x cubed plus 3x to the 5 over 5 minus 3x to the 7 over 7, and so on and so on. And miraculously, these cancel out, and these cancel out. So if you divide the remaining stuff by x to the 5, right, or factor out an x to the 5 from the numerator, you're left with 3 over 5 minus 3 over 7x squared, and then something x to the 4, blah, 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 powers of x, which are even and bigger than 2, divided by x to the 5. These cancel out, and when x is 0, that is 0. Everything's going to be 0 except 3 over 5. How can we, Ren is asking, how can we find the power series representation for something like 1 plus x over 1 minus x all squared? Well, exactly using these techniques. So maybe start with this, or maybe just start with this, and then square it, multiply it by itself, and then multiply by 1 plus x. Yushen is asking for the question on the board, did we conclude that the series is just 0 for all x? That's my claim. We didn't do it in complete detail. You should do the second, third, fourth derivatives. Convince yourselves that all the derivatives are 0. There's probably going to be a pattern emerging that will allow you to conclude that. So many questions. Reza is asking, why is the summation from 1 to infinity of minus 3 to the n plus 1 over negative 5 to the n. What is that? First of all, this is negative 3 times negative 3 to the n over negative 5 to the n, or negative 3 times negative 3 over negative 5 to the n, or 3 over 5 to the n. And this converges to the first term over 1 minus 3 over 5. So what is that? This is negative 9 over 2. Negative 9 over 2? So not negative 5 you're saying, but positive 5? Fine, let's change it. So this is going to be negative then. And then it's first term over 1 minus negative 3 over 5. So that is now 9 over 8. Nine over 8? Well, I mean, look, I'm sure you can figure it out. Let's not, yeah. All right. Moving on. Let's move on. We've already if you're saying it's minus instead of a plus, you're just going to divide by 9 instead. And then you'll get 1 over 8. Yeah, there it is, 1 over 8. All right, let's do 1 or 2 examples from the book, and then we'll move on. All right, you know what to do. Right? First of all, convince yourselves that integration here is not an avenue you want to take, right? I mean, you don't want to try to find an antiderivative for this. Plus, I suspect it can be proven that there is no simple closed form antiderivative for this function. But we're still able to evaluate an approximation to this, right? we're still able to evaluate this correct of 4 decimal places. What are you going to do? Exactly, right? We're going to express sine of x to the 4 as a Maclaurin series. You know you can integrate a Maclaurin series in the interval of convergence. So as long as 0, 1 is in the interval of convergence, we're good to go. Now, on an exam, I would expect you to take 1 minute of your time and work out the Maclaurin series for sine, but we all know what it is, so let's just write it down here. Right, again, I don't expect you to learn these by heart. If this was a regular class and we would have a sit-down exam, I would expect you to have done this so many times that it's second nature to you, that you can do it with your eyes closed in 15 seconds. But there it is. And consequently, and you know that this converges on all of R. The interval of convergence is all real numbers. So if we replace x with x to the 4, this is still going to converge for all real numbers. If you're not entirely convinced, then by all means convince yourselves by applying the ratio test. So Sid is asking if this question came up on the exam, would we need to find the series for sine x again? The answer is yes. So this is the powers multiply, right? This is x to the 8n plus 4. And there it is. You have a power series representation for sine of x to the 4. So it is the Maclaurin series. And if you integrate, and again, you know, this is going to converge on all of R. And you know you can integrate term by term in the interval of convergence. Will a composition of Taylor-Maclaurin series always have the same interval of convergence as the original? Or is it just coincidence? It's actually the smaller of the two, right? This, the function x to the 4, converges for all values of x. The Taylor series representation for sine x converges for all powers of x. I mean, for all values of x, right? This converges for all values of x, right? Because x to the 4 is its own Maclaurin series. So this has interval convergence all of R. This has interval convergence all of R. So when you compose the two, you get interval convergence all of R. Integrate term by term, what do we get? Negative 1 to the n, 1 over 2n plus 1 factorial. Antiderivative of x to the 8n plus 4 is x to the 8n plus 5 over 8n plus 5. And it's a definite integral. When you plug in 1, subtract plugging in 0. When x is 0, these are all powers of x to the 5 and higher. So when you plug in 0, the whole thing is 0. And so we get, what do we get? Negative 1 to the n, 2n plus 1 factorial, 8n plus 5. There it is. This is exactly this integral. That integral is exactly this value. But of course, we don't know what that value is. But we can approximate it. And we want the approximation to be correct to 4 decimal places. So really the question is, how many terms must you add in this series so that the first 4 decimal places don't change? Right? So consider one, two, three, 4, halfway to the next. You know how to deal with that, right? We're going to start by assuming an error halfway to the next, and perhaps adjust need be. Luckily for us, what do we have here? We have an alternating series. And it's easy to see that, the numerator is just 1, and the denominator is getting larger and larger. It's easy to see that it's an alternating series that satisfies the alternating series test. Right? Namely, the denominator is getting larger and larger as n gets larger. And the limit, as n goes to infinity, this goes to infinity, that goes to infinity, so you get a 1 over infinity, which is 0. So you know that you can add, right, let's say this. This minus the sum from 0 to k times 8n plus 5. This is less than or equal to the next term in line. So 1 over 2k plus 1 factorial, 8k plus 1 plus 5. Instead, so Abe is asking, instead of assuming an answer, could we just guess a number of terms to add and use trial and error? Well, I mean, that's exactly what we're going to be doing. That's exactly what we're going to be doing, right? We're going to use trial and error to make sure that this is less than 0.00005 by using trial and error here. Tony is asking if it says 4 correct decimal places, then we need our error to be less than 10 to the negative 5. That's, again, not necessarily true. We addressed that in previous lectures. We're going to see that in effect here again. Yishen is asking if we can use Lagrange approximation. The problem is that we integrated here. And integration is going to be an issue. with the Lagrange remainder theorem. Plus, we never actually calculated the derivatives. And the derivatives are going to be messy here as well. So let's not do that. Can trial and error be considered rigorous in an exam? Well, the answer is yes. And here's why. These terms, as you would have shown normally, I mean, I didn't, I just said it satisfies, but on an exam, you'll have to show that it actually satisfies. These are therefore going to be decreasing. So as soon as you hit one, which is less than that, all the others have to be less than as well. And all we're looking for is the smallest value for which this holds. So 10, 100,000, 10,000, 100,000, this is 1 over 2,000. Right? Is that right? No. 1 over 20,000. And let's try something. If k is 4, what happens? Oh yeah, that's going to be probably fine. Let's try 3. 3 plus 1 is 4. A, that's 9. 1 over 9 factorial. 32, 37. That is very big. I don't know what that is. 5 factorial is 120. 6 factorial is 720. So it's 720 times 72 times 37. That's certainly less than 1 over 20,000. And if k is 2, 3, 6, 7, 1 over 7 factorial, 24, 29. So that's 720 times 7 times 29. 7 times 30 is 210, so that's 203. So it's going to be about 15,000. No, it's going to be that's still. Let me check. Yeah, that's 146,000. So that's still less than 1 over 20,000. We're still good. So k equals 1. If k is 1, so that's 5 factorial, 1621. So that's 120 times 21. That's going to be about 2,000. Well, that's going to be less than 1 over 3,000. It's going to be bigger than 1 over 3,000. Anyways, no good. There you go. So k equals 2 is what we need. We need k equals 2. So we're going to sum from 0 to 2. 0 to 2. Negative 1 to the n over 2n plus 1 factorial, 8n plus 5. Let me again use Wolfram alpha to tell us what that is. Wolfram alpha tells us that this is 0.18, 75, 76, 31, 25, and so on and so on. Carl is asking, would it be wrong if we replace k in the sum from 0 to k by trial and error and check whether the error is within 4 decimal places? Well, here's the question that arises. How do you check that the error is within 4 decimal places? Right? There's no way for you to check if you're just plugging in values of k and doing enough so that you're telling yourself, well, these never change. But have you done enough? That's the question. What if you had to go all the way to 1,000,000 in order for the 4th decimal to change? You don't know. So now we have this, right? When k is 2, the error is, well, 1, 2, 3, right? I mean, look at what happens. If the error was actually this, 0.00005, 00005, if that was the error, then you see that when you add these two things together, that would change the 5 to a 6. And that would not be sufficient. You couldn't conclude that 1875 are the first 4 digits. Luckily for us, by taking this, we actually have an error which is much less than that. It's actually 1 over 146,000. And what is that? That is actually 5 zeros. 5 zeros and 684. So if you have 50684, blah, 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 whether you add or subtract, the 7 could change. It could be a 6, it could be an 8. Who knows? But these 4 will not change. And that's what we wanted. So now we are absolutely sure that the first 4 decimal places are 1875. Brad is asking if we can use a calculator for the last step in an exam. Absolutely, you need that. Does the term with k plus 1 give an actual error or just a bound on the error? It's just a bound. It's just a bound on the error. If you look at the proof following the alternating series test, it was just a bound. Abe is asking, couldn't we have just used the sum in the bottom right corner and see when it stops affecting the first 4 decimal places? This would save a lot of effort. Here is why you cannot do that. What do you know about this series? What do you know about this series? You know that this series is divergent. So you know that if you add these terms from 1 to infinity, you get infinity. So try adding the terms. Eventually, the difference is minimal when you're adding a 1 over n for large values of n. So you start to fool yourselves into thinking, well, I mean, it's not going to diverge. It's going to converge, because eventually, though those terms are insignificant, but they're not. And, right, I mean, imagine 1 over 10 million. It's going to affect 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And 1 over 10 million, it's only going to affect the terms very far from the decimal place. But by adding enough, it in fact affects all of these and past as well. My point is, you don't know. You don't know when it stops affecting. If you're just playing around with this sum, there's no telling when it doesn't affect anymore. Yishan is asking, how do we know if Lagrange multiplier theorem is, remainder theorem is good to use when you found the Maclaurin series and have those derivatives? That's exactly the answer. Amar is asking, doesn't the answer round up to 1876 even without the error? Well, I mean, it's going to round up to 1876, but the 6 is not a significant digit. We wanted 4 decimal places. We wanted 4 significant digits. So you cannot round. Plus, how do you know that by adding enough terms, it could actually be a 6 here. It could be a 7. You don't know until you actually prove it. And that's what we did. So you get us asking, should we give our answer only until 5, like 0.1875, or write the full answer? Well, I mean, whatever. I would write this and say that the first 4 digits are significant. So Tony is saying we want k that will not change the 4th decimal place, and that's exactly right. What if we take a larger value, let's say k equals 10, isn't the first 4 decimal place still correct? It is, absolutely, but we're lazy. We're very lazy. We want the smallest value of k, which works. Notice here, k was equal to 2. So you're really just adding 3 terms. Even if you don't have a calculator or a computer, it's just 3 fractions. You could add those 3 fractions. If this was an actual final exam question in the gym, you could still answer that question and give me a fraction, because you're only adding 3 fractions. So you could give me a right answer, a final answer in terms of 1 single fraction, and that would be and that fraction would be correct to 4 decimal places. All right. Moving on. Let's move on to one last thing with series. The binomial series. What is the binomial series? Perhaps you saw it in the book. Looks complicated. It's nothing. There's nothing there. All it is the Maclaurin series for the function 1 plus x to the k. That's all it is. And the theorem tells us that this is k choose n, x to the n. Where k choose n is k factorial over n factorial n minus k factorial. Or, if you prefer, because, I mean, this is well defined if k is a natural number, right? But if k is not a natural number, then what is that? Well, I mean, you know this to be k factorial is k times k minus 1 times k minus 2 all the way to 1. And n minus k factorial is n minus k, n minus k minus 1, all the way to 1 factorial. And you can cross some of these out, right? These 1's cancel, the 2's, everything cancels until the numerator is really k minus 1, all the way to k minus n plus 1. Let's prove it because again, it's trivial. You know exactly how to find the Maclaurin series for a function. And that's all this really is. Thank you, thank you, thank you, thank you. This should be k minus n. Absolutely, absolutely, I've made a huge mistake. Yeah. This was going to come out in the proof anyways, so it wasn't a big deal, but thank you. We certainly don't want to write anything that's incorrect. Right, what are we doing? We are finding the Maclaurin series for the function 1 plus x to the k. So plug in 0. When x is 0, the whole thing is 1. Differentiate. You know the derivative of this. Nothing fancy is happening here. Just bring the power down, regardless of what k is. Right? This is the answer. So the derivative at 0 is just k. And you keep going until you see a pattern. Second derivative, you know what it is. K minus 1. Second derivative at 0, k times k minus 1. And so on and so on. Third derivative, derivative of this, you bring that to the power. Third derivative at 0, k minus 1, k minus 2. I think you're seeing the pattern here. Quinn is asking, if we integrate a binomial series, is the k choose n not modified? It is not. It is not. You're going to integrate with respect to x. You integrate with respect to x. So x to the n is the only thing that is important. So what are we saying? F of x, Maclaurin series, tells us that this is f of 0 plus f prime of 0 over 1 factorial x. Second derivative at 0 over 2 factorial x squared. And so on and so on. So here, 1 plus x to the k, this is 1 plus k over 1 factorial x. K times k minus 1 over 2 factorial x squared. K minus 1, k minus 2 over 3 factorial x cubed, and so on and so on. And you see the pattern here, right? It's k minus 1, k minus 2, all the way till 1 less than the power. This is x cubed, you stop at 2. X squared, you stop at 1. X to the 1, you stop at 0. So it is what? It is the sum. Well, let's put the 1 outside, because it might not satisfy the pattern. And this is k times k minus 1 all the way to k minus 1 less than the power over n factorial x to the n. There it is. If you choose to adopt the notation in the book, that n choose k business, then that's what it is. So if you go with the n choose k, k choose n rather, and it turns out that if n is 0, this also works. If n is 0, everything is 1. So if n is 0, this notation also works. And there it is. You don't need to remember this. And you don't need to remember this either. All you need to do is remember that you can work it out. You don't need to learn these formulas. You can take 1 minute and work it out. This is just the Maclaurin series for this function. That's all it is. Right? Well, I mean, when n is 0, here, what is this? This is k times k minus 1 all the way to k minus n minus 1. So if n is 0, this is 0 minus 1, so you get k plus 1, which is actually bigger than k. So it's problematic. This notation is problematic when n is 0. It works when n is 1, but when n is 0, it doesn't work. If k is equal to 1, or any other integer for that matter, would the sum not be 0? Eventually the terms would be 0, right? Very nice observation. If k is an integer, a natural number, a positive integer, if k is a natural number, then eventually this product is 0. So eventually the terms are all going to be 0 for n large enough. So what you're suggesting is that you actually get a finite series, which makes a lot of sense, right? Because if k is a natural number, let's say k is 6, what are you really working with? You're working with 1 plus x to the 6. And if you expand this, you get a polynomial, right? This is x to the 6 plus other stuff all the way to 1. You get a finite polynomial, which is its own Maclaurin series. So the Maclaurin series should be finite. And it absolutely is, because eventually the numerator is going to be 0. All right. How are we doing here? Questions? Anybody? This is the end of series. If you have questions, you could ask them now. Any questions on series? We'll spend the rest of the lecture doing a quick review of linear algebra, if there are no questions on series. Yushen, I'm not sure what you're asking here. What we're saying is that if k was a natural number, eventually this numerator would be 0. Amar is asking if a series does not satisfy all the conditions of the alternating series test, can we conclude that it diverges, or is the result inconclusive? It depends what condition. If the limit is not 0, the divergence test takes over and the series diverges. If the limit is 0, but the terms are not decreasing, then the alternating series test is inconclusive. The series could still converge, it might diverge, you don't know. So Yushen is asking, when k is a natural number, why is the numerator 0? Well, convince yourself, right? But let's say this example, if k is 6, what are we looking at? K minus 1, all the way to k minus n minus 1 over n factorial. This is from 1 to infinity. Let's write out the first few terms. When n is 1, n minus 1 is 0, so you're stopping at k. So it's going to be k over, well, I mean, here k is 6. Well, yeah. So 6 over 1 factorial x to the 1. When n is 2, you stop at k minus 1. So it's k times k minus 1. So it's 6 times 5 over 2 factorial x squared. And then 6 times 5 times 4. 6 times 5 times 4 times 3. You see what's going to happen, right? And then it's going to be 6 times 5 times 4 times 3 times 2 times 1 and then times 0. And from then on, it's always 0. Tony is saying, if k is a natural number, the series will always be 0. Well, not in the beginning, right? In the beginning, you'll have some finite terms, but eventually all the terms will be 0. So it's going to be a finite sum, not an infinite one. Amar is asking, how can we determine the convergence or divergence of something like this? You know what to do, right? Cosine n is always between -1 and 1. So 1 plus cosine n is going to be between 0 and 2. And if you multiply by 1 over e to the n, you get that 1 plus cosine n over e to the n is bigger than 0, but less than 2 over e to the n. And this is a convergent geometric series. So if the bigger one converges, then the smaller one converges by the comparison test. While we're talking about these kind of series, let me share with you something I shared with the 141 class. So if you were in 141, you may have seen it. It's a beautiful result that I proved over the Christmas break, which gives you hope that there are still some nice, simple proofs out there. Consider the series n a to the n, where a is less than 1 in absolute value. We know this converges. You can test for convergence using the ratio test, and ratio test will give you convergence. In fact, you know you can actually figure out what this converges to now that we have experience with Taylor series, right? Using Taylor series, you know that x to the n is the series 1 over 1 minus x, if x is less than 1. You know that you can differentiate in the interval of convergence. So if you differentiate n x to the n minus 1 is the derivative of this, which is 1 over 1 minus x all squared. And if you multiply both sides by x, you get n x to the n is x over 1 minus x all squared. So this series actually converges to a over 1 minus a all squared. Very nice. I did not prove this. This is the usual method to prove what the series converges to. But this makes use of Taylor series and differentiation and all of that stuff. Nothing wrong with that. But I came up with a nice, simple solution, and somebody sent me an email last week as well with a similar approach, which was very nice. Instead of looking at n a to the n, look at n plus 1 a to the n plus 1. By making a change of variables, right, if you let k be n plus 1, this is really n a to the n, where you're starting at 1 instead, right? Just a dummy change of variables. And there it is. But this you can split up into two things. N a to the n plus 1 and 1 a to the n plus 1. And if you factor out an a from each of these, this is the same thing, right? Here, when n is 0, the whole thing is 0. So I could change that to a 0. And the first term is 0, it doesn't matter. And even if it wasn't, you could still adapt it. There'd be no issue. So there you have it. What are we saying? Well, I mean, first of all, this is a geometric series, so you know exactly what this converges to. This converges to 1 over 1 minus a, if a is between -1 and 1. So this is equal to that. Let's rewrite that here. What are we saying? So this over there is equal to that. So I've got an A here. Bring this to the other side, right? This is the same as that. So here you've got a 1. So 1 minus A times the sum is equal to that. And divide by 1 minus A, you're done. Beautiful. Beautiful in its simplicity. Nothing was assumed. No Taylor series, Maclaurin series business. This comes out naturally. And this can be extended. This can be extended you can do the same thing with n squared by looking at n plus 1 squared, an plus 1, and n cubed, and n4. And in fact, you can extend to any polynomial. So using this simple trick of n plus 1 instead of just n. So how are we doing? Questions here? Perhaps I should mention that not only can you extend it to polynomials, you can throw in sines and cosines here. Or cosine. That a small adaptation is going to work. You're going to use the fact that sine of n plus 1 is sine n cos 1 plus cos n sine 1. The sum and difference identities for sine and cos, everything generalizes nicely. All right. Questions? All right, is asking, do we have to use a squeeze theorem to prove one is bigger than the other? In the case we showed before, I think it's the way to go. It's not really a squeeze theorem, right? It's a comparison test, but there it is. Valentina is asking, how do we calculate the sum of a convergent series? Well, I mean, it depends what the series is. Can we find this proof in the textbook? You cannot. I have never seen it before. And I spoke to a few professors. They were not aware of this either. Why is the initial index 0 when we substitute for n plus 1? Well, I mean, I was saying you start having this at 0. And then when you make a change of variables, k is n plus 1, then you actually have n squared an, and this would start at 1, but you can make it start at 0 if you wish, because when n is 0, the first term is 0 anyway, so you're just adding a 0. There's no harm done. All right, let's quickly discuss a bit of linear algebra. How are we doing with linear algebra? Do we have any questions? Vectors and all that stuff? Do I need to discuss the dot product, cross product, and so on? Are we comfortable with that? Do we want to refresh? We want a refresher on that, or anybody? There are no questions. Yeah, absolutely. Everything's covered in 133. If there are no questions about cross product and dot, what? Well, Rebecca is asking for yes, please. So let's do it then. Let's recall. Do we need anything beyond matrices? It depends what you mean by beyond. We're not touching matrices at all. So let's recall. So I mean, you know, we have a good half hour left. I'm sure we can do a ton of things. There are no matrices in this course essentially. So nothing to do with matrix multiplication, but rather vectors themselves. Let's recall that a vector is a quantity with both direction and magnitude, right? So a vector can be represented by an arrow. The direction is the way the arrow is pointing, and the magnitude is represented by the length of the arrow, right? So this is a vector. This is a vector. This is also a vector. Notice that here these two vectors are pointing in the same direction and they have the same length. And a vector is defined by length, magnitude, and direction. So if these are both pointing in the same direction and both have the same magnitude, they must be the same vector. These two vectors are the same vector. You can move vectors around. That's what we're saying. And if you bring them to a nice setting, the xy plane, these two vectors, which are the same, you can move them, and as long as they point in the same direction and are of the same length, then they are the same vector. In other words, you can, without loss of generality, assume that they emanate from the origin. And consequently, the only thing of interest is the endpoint. So you can confuse a vector emanating from the origin with its endpoint, AB. The magnitude, right? So if you have a vector emanating from the origin to the point AB, if you have a vector starting at the origin going to the point AB, then we're going to say that that is the vector AB. And if you look at the Pythagorean theorem, right, this point AB means you go A in the direction of X and B in the direction of Y. And so by the Pythagorean theorem, the hypotenuse has length square root of A squared plus B squared. And consequently, we say that the magnitude of the vector AB, namely the vector that starts at the origin and goes to the point AB, has length square root of A squared plus B squared. Given two vectors, AB and CD, we define the dot product. So AB dotted with CD to be the product of the first components plus the product of the second components. I'm doing this in R2 in the XY plane. Of course, you know that it extends to higher dimensions. Theorem, as you know, the dot product is really the length of V, length of W, times cosine of the angle between the two. And we say that V and W are perpendicular or orthogonal if the angle between the two is 90 degrees or pi over 2. In other words, V and W are orthogonal if and only if the dot product is 0. Right? Because if the angle between the two is 90 degrees, cosine of 90 is 0. Let us do a few exercises from the book. We are asked to calculate A dot B. We can do that in our heads, right? This is 12. Minus 10 is 2. Minus 3 is minus 1. If A is 3i plus 2j minus k, and B is 4i plus 5k, let's remind ourselves that I is the vector 1, 0, 0, j is the vector 0, 1, 0, and k is the vector 0, 0, 1, meaning that this is the vector 3, 2, minus 1, whereas this is the vector 4, 0, 5. Isn't it minus 5 for A dot B, you mean? What do we get? 12 minus 10 is 2. 2 minus 3 is minus 1. I want to say minus 1. Right here, A dot B. What is A dot B? 8 plus 0 is 8. Minus 5 is? 8 minus 5 is 3. It's all good? We are asked to find the angle between right, this is 1 minus 3, and this is minus 3, 4. We don't know if we're in 3D or 2D. Who knows? Isn't it the other way around? Isn't A 3, 2 minus 1? Yes. Yes, yes, it is. Not sure what happened here. 3, 2 minus 1, thank you. And 4, 0, 5. So that changes the dot product. 12 minus 5 is 7, thank you. Absolutely. Absolutely. Here, what are we going to use? We're going to use the fact that the dot product A dot B is length of A, length of B, cosine of the angle between the two. So A dot B is what? Minus 3 minus 12 is minus 15. Length of A, this squared plus this squared, square root. So that's square root of 10. Length of B, 16 plus 9 is 25. Square root of that is 5. Cosine of the angle between the two. So we see that cosine of the angle between the two is minus 3 over root 10. And consequently, theta is the inverse cosine of minus 3 over root 10. Whatever that is. An important operation on vectors is the idea of projections. Suppose you've got a vector v and a vector u. Suppose you have a vector v and a vector u. We can discuss the projection of u onto v. Imagine shining a light in a direction perpendicular to v, so that this u is going to cast a shadow onto v. We want to know what is this vector. This is the projection. This shadow here is the projection of u onto v. And as you see, it's really a vector in the same direction as v. So it has to be a multiple of v. And you can work it out using this idea. But what multiple of v is it? It's u dot v over the length of v squared. So it's this multiple of v. You can prove it using geometry, right? It's really just a cosine. Really the question is, how long is this? You can work that out. Let's take an example. Right, this is just review. You've seen all of this anyways. We are asked to find the projection of B onto A, where B is this vector and A is that one. So projection of B onto A is going to be a multiple of A. What multiple? Well, the dot product. So minus 12 plus 16 is 4, plus 4 is 8. So that is 8 over the length of A squared. 64 plus 16, that is 80, 81. Length of a squared times a. There you go. It's a multiple of a. This multiple right there. Questions here? Moving on to the cross product. Given two vectors in R3, right? If you're in R3 and you're given two vectors, then there exists essentially a unique one which is perpendicular to both. Right? I mean, either this one or the one going down, but essentially they're just multiples of each other anyways. So given two vectors, let us define the cross product. And here I'm going to give you the shortcut for the cross product, which I'm sure you know anyways, right? So U cross V is just the determinant of the remaining 2 by 2 matrix if you remove the first column. So the first component, BF minus CE. Second component, remove the second column, AF minus CD, and then take negative of that. And third component, AE minus BD. Let's take an example. You can prove that this cross product here is actually orthogonal to both the original vectors. Consider these two vectors. We are asked to find the cross product and show that the cross product is orthogonal to each of A and B. So let's work that out. First component, 3 minus 2, that's a 1. Second component, 4 plus 4 is 8. And change the sign. Finally, minus 4 minus 6 is minus 10. Is this correct? Well, I mean, Amar and Martin, you should know, you should have seen this before, right? You should know what the cross product actually gives you. But as Prüm suggests, it is AE minus BD. So minus BD, atom, yeah. Here's the proposed cross product. Is this correct? It should be orthogonal to each of the two original vectors. So 4 minus 24 is minus 20. Plus 20 is 0. Very nice. 2 plus 8 is 10. Minus 10 is 0. There you go. You know you're right. Similarly to the dot product, where the dot product was length of A, length of B, cosine of the angle between the two. Here, the length of the cross product is actually length of A, length of B, sine of the angle between the two. Geometrically, what does that mean? That means that the length of the cross product is actually the area of the parallelogram determined by U and V. This is the area of the parallelogram by A and B in this case. And we had given a definition that U and V were orthogonal if the dot product is 0. We can ask ourselves, when is the cross product 0 here? And the cross product is going to be 0 if the angle between the two is 0 or 180 degrees. In other words, if the two vectors are parallel. Let me end with the following observation. If you have three vectors, U, V, W, then two vectors determine a parallelogram, right? Because this vector is the same as that one, and this one is the same as that one, and this W is the same as this one, which is the same as that one, which is the same as that one, and this V is this V, and that V, and that's U, and that's U. What are we saying? Three vectors determine a parallelepiped. And the volume of this parallelepiped is the absolute value of U dotted with V cross W. Or any, you can interchange any of these vectors. That's why we have the absolute value there. Now, as you know, any straight line is completely determined by 2 points. There's only one straight line going through these 2 points. And there it is. In the context of vectors, though, observe that if you're given 2 points, P and Q, you really have a vector joining the two. You have this vector PQ. And every point on the line, if you take a point XYZ on the line, then every point from P to XYZ is really a vector that is parallel to the vector PQ. So every point on the line which is a vector XYZ minus P, must be a multiple of the vector PQ. So every point XYZ is P plus T PQ. This is the equation of a line in parametric form. This is how you describe lines in general. Let's take a few examples. We are asked to find the equation of a line We are asked to find the equation of a line through these 2 points. So let's find the vector joining the 2 points. This will give us the vector PQ, also known as the direction vector. Right, so the vector joining the 2 points, or the direction vector, one minus the other, 1 minus -5, 6 minus 2, and minus 2 minus 5. Here's your direction vector, and every point on the line has the form XYZ is 1 point plus t times the direction vector. As you know, this is not unique. Here we did this one minus that one. You could have just as easily have done this minus that. So your direction vector would have been negative of what we had. And instead of choosing the point 1, 6 minus 2, you could have taken that point. So you really have 4 possible answers here, 4 immediately possible answers. There are, in fact, infinitely many, but there it is. So the equation of a line is not unique, but the collection of the points making up that line will be the same. Let's do a few more. Still the same question. Here it is. We're looking for the line through the point 2, 1, 0. And that line should be orthogonal to both these vectors. What does that mean? That means that the direction vector in particular should be orthogonal to both of these. But I plus j is the vector 1, 1, 0. J plus k is the vector 0, 1, 1. So a vector orthogonal to both we can use as the direction vector. And what vector is orthogonal to both of these? One minus 1, 1. Let's check. Dot product, 1 minus 1 is 0, plus 0 is 0. 0 minus 1 plus 1 is 0. This vector is orthogonal to both. The equation of the line is a point 2, 1, 0 plus t times the direction vector. There it is. We haven't defined these objects yet, but you know very well what they are. These two things are planes, right? Flat, two-dimensional surfaces which extend forever, right? So like two large pieces of paper, right? You've got one plane here, you've got one plane here. The intersection of the two is a straight line. The intersection of the two is the set of points x, y, z which satisfy both equations. And you know exactly how to solve for that, right? You can put these in a matrix. Now I know what you're thinking. I just said there wasn't going to be any matrices. Clearly I was wrong. We have a matrix right there. You know what to do. You're going to row reduce to reduce to echelon form. This minus that. This minus that. Change that into a 1. And finally, use this one to get rid of that 2. Row 1 minus 2 row 2 for row 1. So this minus 2. So 9 minus 4 is 5. And there you have it. X and Y both have leading ones, Z does not. So we replace Z with a parameter, T. X is 1 minus 5 over 3t, and Y is minus 2 over 3t. Exactly the equation of a line as you know it. Beautiful. How are we doing? Let's take a few remaining moments to discuss exactly these things, these planes, geometrically. Right? Geometrically, these are flat surfaces, infinitely large in both length and width, if you will. And on these surfaces live vectors. These are two-dimensional objects, right? It has length and width. You can describe them as a linear combination of two vectors that live on the plane. Now, instead of describing it as a linear combination of those two vectors, if we're in 3D, why not just describe the essentially unique vector, which is perpendicular to each of these? Right? If you have u and v, there's essentially just one vector which is orthogonal to both, namely the cross product. Of course, multiples of this will also be orthogonal to both, but it's just multiples of the same vector. So we're going to describe not the two vectors that live on the plane, but rather the one that is orthogonal to both, and we're going to call that the normal. And if you have a plane through some point P, any point on the plane, x, y, z, produces a vector from the point P to that point, and that vector, x, y, z minus P, has to be orthogonal to the normal. And that gives you the equation of a plane. If the normal has coordinates a, b, c, then the plane has equation ax plus by plus cz equal to some number. That comes from right here, right? This is ABC. So you get ax plus by plus cz minus the normal dotted with the point, and that's going to give you the value d. Let's take a few examples. We are asked to find the equation of a plane through the point minus 3, 4, 2 with normal 6, 1, minus 1. An easy question to begin with. You know what to do. Your normal is 6, 1, minus 1. So immediately, the plane must have equation 6x plus y minus z equal to something. You can work out what that something is by making sure that the point minus 3, 4, 2 lives on the plane, so that it satisfies the equation minus 18 plus 4 minus 2 must be d, so minus 20 plus 4 minus 16. In other words, 6x plus y minus z is equal to minus 16 is the equation of your plane. Same question, we're looking for the plane through the origin. Perpendicular to this object, whatever that is. Well, you know what that is. You recognize this as a line. Let's draw a picture of what's happening. You want the equation of a plane that is perpendicular to a line. You know, in order to define a plane, all you really need is the normal. So the normal, right, Here, when you're given a line, you're really given a direction vector. And the direction vector needs to be orthogonal to your plane. So the direction vector should be the normal to your line. What is the direction vector here? The direction vector is the coefficients multiplying t. So direction vector minus 8, minus 7, 2. So your plane has equation minus 8x minus 7y plus 2z equal to d, whatever d is, and you're going to find d by plugging in a point. Now, the question tells you the plane goes through the origin. So it goes through the point 0, 0, 0. So d has to be 0. In other words, minus 8x minus 7y plus 2z equal to 0 is the equation of the plane. Let's do one more. And then I'll tell you where we're headed in the course. Plane through 9 minus 4 minus 5, parallel. Parallel to this. What is that? You recognize this. If you bring this over to the other side, this is minus 2x plus 3y plus z is equal to 0. You recognize this as a plane. So what do we want? We want the two planes to be parallel. If two planes are parallel, then their normals should be parallel, or in particular, the same. So we're going to take the normal to be the same normal. 2, 3, 1. So the equation of our plane, minus 2x plus 3y plus z is equal to d. All we need to do is make sure that this point lies on the plane. That is minus 18, minus 12, minus 5, so minus 35. In other words, the equation of the plane we wanted was minus 2x plus 3y plus z is minus 35. How are we doing here? Questions? Anybody? Where are we going with this? Our aim is to extend the ideas of calculus to higher dimensions. We're going to extend the idea of differentiation. Why we use the dot product to find d. I am not using the dot product. I am plugging in this point into this equation of the plane. I want to make sure that that point lies on the plane so that it satisfies the equation of the plane. So when x is 9, y is minus 4, and z is minus 5, It should be a point on the plane. So our goal for the rest of the course is to extend the notions of calculus to higher dimensions. Differentiation in several variables. Integration in several variables. That's what we're going to look at next. So tomorrow we'll start with something easy-ish. To get a feel for functions, we're going to try and graph some functions in 3-space. We'll see a nice way to approach that. It's not as difficult as it seems. So we'll tackle that tomorrow and move on from there with the exactly how we started in calculus. If you think back, in Cal 1, we started by looking at limits in order to define the derivative, and we're going to do exactly that tomorrow as well. We're going to start with limits in higher dimensions, and then we're going to use that to define the derivative. So I'll see you then, unless there are any questions. Anybody? Thank you all for coming. I will see you tomorrow. Oh, Benit is asking a question. Yeah, I know you sent me an email. I'll get to it. The issue is that it was final exam season for us. So I was very busy marking final exams. And now that we have finished marking final exams, I have to release the grades. And now yesterday, in a 3-hour period, I got something like 60 emails that I still have to get to. And now I suspect that I'll have at least 60 more. You can say that, absolutely. The problem is if you look at the P-series test that we looked at, it's really it really follows from the integral test. And in the integral test, you need your function to be decreasing, continuous, and positive. So I guess you're fine with 1 over n to the 0. That's decreasing-ish. It's fine. So the answer is yes. More importantly, though, the divergence test will give you the result immediately. The limit is not 0, so we're done. What materials will be on the final? Certainly all of chapter 11. Of course, all of 11. I haven't written it yet, but certainly everything we did today, probably what we do tomorrow and Thursday as well. You know, since it's open book and it's only going to get released on Friday, you should keep up to date with the material, and whatever we cover on Thursday, you should learn it Thursday afternoon to be ready for Friday's exam. Let's say that. All right. Thank you very much. I'll see you tomorrow.